Hey Algebra 1, continuing in our function units. Today we're going to talk about the graph of a function. The first slide is going to be a lot of words that I'm going to read through and discuss with you guys. It's really small too. So in Module 1, that was Unit 1, we graphed equations like y equals 10 minus 4x by plotting the points in the Cartesian plane by picking x values, then using the equation to find the y value for each x, the pair. The number of ordered pairs you plotted to get the general shape of the graph depended on the type of equation. Linear, which is a straight line, quadratic, which is a parabola, etc. The graph of the equation was then a representation of the solution set. It was a way to show the solution set, which could be described using set notation. In this lesson, we extend set notation slightly to describe the graph of a function. In doing so, we explain a way to think about set notation for the graph of a function that mimics the instructions a tablet or laptop might perform to draw a graph on its screen. What we're going to do today is like computer programming. It mimics it. So if you're a programmer, don't laugh at us non-programmers, but this mimics what a computer would do to draw a graph on a screen. So getting into it, exploratory challenge 1. Computer programs are essentially instructions to computers on what to do when the user, you, makes a request. For example, when you type a letter on your smartphone, the smartphone follows a specified set of instructions to draw that letter on the screen and record it in memory as part of an email, for example. One of the simplest types of instructions a computer can perform is the for next loop. Below is a code for a program that prints the first 5 powers of 2. So let's declare x as an integer. If you remember, an integer is individual numbers like 1, 2, 3, 4, 5. And then we can say for all x from 1 to 5, so we start at 1, we end at 5, print 2 to the x power, and then next. So it's a for next loop. So for this stuff, next x. It goes back up to the beginning. So for x equals 1, print 2 to the first power, next x. For x equals 2, print 2 to the second power, next x, etc. And that is your output. So it's really going, it's like what we did previous. I can say n equals 1, n equals 2, n equals 3, but that's really not what we're doing. It's just picking x's from 1 and inputting them into 2 to the x and then getting your answer. 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power. So this is your input, or your domain, and that is your output, or your range. Here's a description of the instructions. First, x is quantified as an integer, which means the variable can only take on integer values and can not take on fractions or irrational numbers. The for statement begins the loop, starting with x equals 1. The instructions between for and next are performed for the value x equals 1, which in this case is just to print 2. Print means print to the computer screen. Then the computer performs the instructions again for the next x equals 2. That is print 4, and so on until the computer performs the instructions for x equals 5. That is print 32. And then it is done. It has satisfied its loop. Perform the instructions in the following programming code as if you were a computer. And your paper was the computer screen. So declare x an integer. For all x from 2 to 8, print 2x plus 3. So first I'm going to do x equals 1. X equals 2 because we're from 2 to 8. 2 times 2 is 4, plus 3 is 7. So that's what I'm going to print first. And then 3 times 2 is 6. Plus 3 is 9. When x is 4, we've got 11. When x is 5, we have 13. X is 6. X is 7. And x is 8. That is what the computer screen would print. So I added this because there's a word in this lesson that I don't use it in vocabulary often, and it's append. It means to add something as an attachment or supplement. The results of the survey are appended to this chapter. Synonyms are attach, add, affix, tack on, tag on. I don't know what subjoin means. The teacher may append comments to the final report. So you're adding something on. So exploratory challenge 2. We can use almost the same code to build a set. First, we start a set with 0 elements in it called the empty set. Then we increase the size of the set by appending or adding on one new element to it for each for next step. So this example is declare x as an integer, that means they're all whole numbers. Initialize g as your empty set. And then for all x from 2 to 8, append 2x plus 3 to g. So we're adding it to the set. And then print g, next x. So note that g is printed to the screen after each new number is appended. Thus the output shows the set builds. So the first one is 7, and then 7 and 9, and then 7, 9, and 11. So we're appending each additional element to the set and building it bigger and bigger and bigger until you've used all of your integers from 2 to 8. Let's try one. We can also build a set by appending ordered pairs. Perform the instructions in the following programming code as if you were a computer and your paper were the computer screen. The first few are done for you. So declare x as an integer and initialize g as an empty set. Then for all x from 2 to 8, we've got append x and then 2x plus 3 to g. Print next x, print g. So you see our set is building in ordered pairs where we get x and then the value that matches with x. This would be 2x plus 3. X, and then 2x plus 3. X, 2x plus 3. X, 2x plus 3, and x, 2x plus 3, until you run out of integers. We can also graph our answers instead of building a set where we would print it on a Cartesian plane, or as the computer would here, we would plot our set. So we're going to plot x and then 2x plus 3 from 2 to 8. And our output is 2, 7. That's what we have in the previous screen. 2, 7, that's a comma, 3, 9, 4, 11, etc. And notice they are all dots, not connected by a line. They're in a linear fashion, but they aren't actually connected. So in mathematics, the programming code above can be compactly written using what is called set notation. Set notation is important. It's important for you to be able to read and to write. So what we have here is a set x, 2x plus 3, such that x is an integer and x is between 2 and 8, including 2 and 8. This set notation is an abbreviation for what I just said, but that's okay. The set of all points, that's what these little bracket thingies mean, the set of all points, x and 2x plus 3, such that, that's this line right here, such that x is an integer and between 2 and 8. Notice how the set of ordered pairs generated by the for next code above is given. I've still got the set of all points written in. Also satisfies the requirements described by the set of all points, x and 2x plus 3, such that x is an integer and between 2 and 8. It is for this reason that the set notation of the form type of the element, such that condition on each element. This is what we're working towards. Okay? It's important. It's called set builder notation because it can be thought of as building the set just like the for next code. Now we can upgrade our notion of a for next loop by doing a thought experiment. Imagine a for next loop that steps through all real numbers in an interval, not just the integers. No computer can actually do this. Computers can only do a finite number of calculations, but our human brains are far superior to that of any computer, and we can easily imagine what it might look like. Here is some sample code. So we're going to declare x as real, not an integer anymore. So declare x real, and then let f of x equals 2x plus 3. Initialize g as an empty set for all x such that x is between 2 and 8, but they're real, so they're all the numbers between 2 and 8, an infinite amount of numbers between 2 and 8, not just the integers 2, 3, 4, 5, 6, 7, 8, but 2.1, 2.2, 2.3, 2.3, 1, 4, 5, 6, 7, 8, etc. So all x. Append x and then f of x to g. Next x, plot g. So the output for this thought code is a graph of x for all real numbers, x in the interval. Here we don't have dots. We have a line, which is an infinite amount of dots connected to each other. Plot the function of f on a Cartesian plane using the following for next thought code. So this time x is real, we have a parabola, and then initialize g as an empty set. We're going to go from -2 to 3. Hold on, let me get my thicker pen out. It's easier to plot. Append f of x to g. Next x, plot g. So I'm going to actually plot, well, let's go through. Yes, I'm going to plot the integers and then connect the integers to make it all real numbers. So if I put -2 in there, -2 squared is 4 plus 1 is 5. So we're going to come up here. -1 squared is 1 plus 1 is 2. 0 squared plus 1 is 1. And then I know that it just mirrors over. 3 squared is 9 plus 1 is 10. So I start here. Now it's all real numbers. Oops, I went too far. It's all real numbers, so I can make a curve out of this. It's not just dots. For each step of the for next loop, what is the input value? The input value is all real numbers. X. For each step of the for next loop, what is the output value? The output value is f of x for x squared plus 1. The domain is all values between -2, all real values between -2 and 3. And the range, I'm going to go back and look. Hold on. All right, the range is very easy to find when you've graphed it, because the range is the output or the y values. And I can look at just the y-axis and decide that the range goes from 1 to 10, because I looked at my y-axis. That's a 1 and that's a 10. Cool. Closing. The set of all G built from the for next code in exercise 4 can also be compactly written in mathematics using set notation. The set of all real numbers, x and x squared plus 1, such that x is real, not an integer, it's real, -2 to 3. Okay, we know this is going to be a graph where things are connected, not just points plotted. When this set is thought of as plotted in the Cartesian plane, it's the same as a graph. When you see the set notation in the problem set and or future studies, it's helpful to imagine this set builder notation as describing a for next loop. In general, if your function is d goes to y as a function with domain d, then its graph is the set of all ordered pairs given, where x is an element of d. It's thought of as a geometric figure in a Cartesian plane. The symbol E simply means in. The statement XED is read X in D, and I always read it as X is an element of D. Good work. That's it. Nice job.